And also, I would like to thank Mark for his excellent introductory talk, make my life much easier. So what I'm going to do, to take over from what Mark has been talking about, to say something about how we put everything together to form this whole heart model. So first of all, I would like to show this elegant slides from Latel group. What is shown here, this is normal electrical activity of the heart. So the heart actually is a sequence of muscle mechanical contractions. This muscle contraction is initiated by a sequence of electrical waves. This electrical wave is first initiated in a special region called the synuclein node, which is the pacemaker of the heart. Once it's initiated, so then it propagates towards this atrium, then towards this AV node, which is the connection between the atrium and the ventricle part. Then why this propagating fiber network to excite the whole ventricle. So this is the excitation sequence of this normal exciting wave in the heart. The heart actually is inhomogeneous tissue with these cells in different regions have different electrical properties. Let's say this synuclein node action potential is markedly different from this atrial action potential and so on. So then this electrical propagation are well coordinated, which can be reflected by this ECG, with this P wave corresponding to the activation of this atrium, then this QRS wave here corresponding to the activation of the ventricle, and this T wave here corresponding to the repolarization in the ventricle. Okay, so this is demonstrating this really complicated structure of the heart. To put everything together, what we need to consider here now is, first of all, to consider the electrophysiology, which show markedly heterogeneity into the heart. And also, we need to think something about this anatomic structure. And we started to do something about this elastic mechanics now, try to make this model's contraction. And in the future, we hope we can get something about this fluid mechanics incorporated into the model. So what I'm going to talk to in the next few minutes is about the work we have done to construct this virtual rabbit heart. So this heart is complicated. This complication is determined by this structure and also this electrical properties. Structurally, you can see these heart cardiac cells in different regions called different morphology. So this is the typical ventricle cell type. This is the atrium, which shows this rod shape. But for the synuclein node, for the AV node, and the center of the synuclein node, you see this morphology is markedly different to this ventricular. And also for the propagating fiber cells, you can see it's a non-cell type, which may be for the purpose of the conduction. And also for the cell diameters, such as the length and the radius, are markedly different from different regions to different regions. So at a molecular level, this heart also shows this complexity. In our lab, we have systematically measured this messenger RNA expression level for these proteins coding this sodium channel, this L-type calcium channel, and then this IF here, IKR, IKS, and IK1, all show this kind of different kind of levels of this heterogeneity for these proteins coding these ion channels. So at this, for this central and the peripheral synuclein node, you can see this sodium channel are very small, and for this atrium here, this sodium channel is relatively large, and also for the AV node here, this sodium channel is marked very small here. To this propagating fiber and to the ventricle, there's a change again. So this shows beautiful kind of patterns for this kind of messenger RNA level. At this ion channel level, this also shows this kind of marked differences for the sodium channel and for this L-type calcium channel, and also for this L-type T-type calcium channel and IF here. So what we've done here, we searched enormously from the literature, get the experimental data for the current densities of the channel, for the cell type, for the center of the synuclein node, peripheral of the synuclein node, atrial muscle, AV node, then this propagating fiber, and this ventricle. So this experiment data was done by different protocol. So then what we did here, after we use the bar to construct this mathematical model, so use the same kind of protocol for us done experimentally. Then with the model, we can have this kind of a uniform protocol for these different cell types. You can see still show this kind of distributions. So this data are obtained from some from our lab here, some from this exhaustive kind of literature searching. So for the sodium, for the L-type calcium, and for this T-type and IF. For this output currents show also similar kind of distributions. So this simple here, experiment data, this open bar here are the modeling data. With this uniform kind of protocol, you can see also this kind of complex pattern through the whole heart. So this also obtained from the different labs, and some are done in our lab. So then with this model, we developed a family of these mathematical models. For this kind of a signature node, we have a center and the peripheral. For the atrium, we can seven different cell types. For the AVA, as Mark has talked about, we have 3 different cell types. We also develop a model for the Purkinje fiber, AP, middle, and endo for this ventricle. So from here, we select kind of 10 of these models to construct the whole heart model. So what we got here, this 10 model here, we got a signature node 1 for the center and the peripheral. Then this actually is the model generate action potentials. This need to insert here experimental data. So you can see kind of a matching between this simulation action potential and this experimental data. So then for the atrial muscle, then for this atrial ventricular node model, then for the Purkinje fiber, for this ventricle model. Then we validated this model to compare this kind of characteristics, such as action potential durations and this maximal upstroke velocity, maximal diastoling potential, this amplitude. So this simple here are the experiment data, and this bar here are our modeling data. So then we also validate the model by compare this kind of pacemaking cyclins for this pacemaking cells for the center and the peripheral. So this solid symbol here are the modeling data, this open symbol are experimental data. And also compare the exab cells with these APT resting curves, as what Alan has said. For this kind of crus terminalis, which is the atrial muscle, for this Purkinje fiber, and this is for the AP, endo, and middle ventricle cells. So then what we do with this kind of a family of these single cell models, we consider this kind of conduction pathways through the whole heart. What we consider here, we take this kind of one strand of this main conduction pathway from the central signature node to peripheral, then to the crus terminalis, to the AV node, then to this Purkinje fiber, and this to the ventricle. Then we put them there into this kind of one-dimensional strand model of the whole heart. So then we have this kind of the size for each region is given by this anatomical kind of data. So then we have this whole heart model. Then we can have this kind of gradient distribution or kind of heterogeneity for this cell capacitance from this is distance again plot against this kind of capacitance gap junction coupling, and this is the model data we used. This symbol here I experimental data. So then we validated the model by plot this activation time. So this solid line here are this computing data. This solid here experimental data for this activation time and also for this averaging velocity. So you can see the signature node first the initiated action potential propagated from center to the peripheral, then the atrial muscle, then this AV node. We got the fast pathway, then this slow pathway, then this Purkinje fiber, then this ventricle. So from there, we can simulate this ECG. So this is initiation and propagation of this electrical waves through this 1D whole heart model. Then we can simulate this conduction and also calculate this ECG. This is the P wave, this is the QRS, then this is the T wave. So we can reproduce this kind of ECG profile. Then we want to test whether this model works or not. Then what we go one step further, we consider the effect of this acetylcholine to the model to see how this acetylcholine changes the profile of the ECG. So this black line here are the control case. So this gray line here are with the application of the acetylcholine. So from here, we can calculate this PI interval, which is from here to here, then this QT interval, which is from here to here, then this RI interval, which is from here to here. You can see with the control and with the acetylcholine, this RI interval is markedly increased. Then this QT interval is also increased, but this PI interval is increased slightly. So this is our model prediction. Whether or not this model is right, we done one step further. We use this Langdorf whole heart. Then we apply something like acetylcholine, but it's non-degrading chemical. So we put this chemical here, we can record this ECG, then we get this experimental data for the control, for this acetylcholine, then we can compare. Okay, so for this RI interval, so these two are experimental data for this control, then for this application of acetylcholine. Our predictions are quite fitting to the experimental data. Then what we did one step further, to see what's this kind of mechanisms underlying the correlation between RI interval and the QT interval. In his recent editorial remark, he said that this well-known correlation between this RI interval and the QT interval. So then we will use the model, we put acetylcholine in the stochastic way, then we can see simulate ECG for 100 seconds. Then we measure this RI interval, QT interval, and the PI interval. Then we plot this RI interval and the QT interval. We find that this kind of correlation shows beautifully this IPD resting curve, but PI interval doesn't show this correlation. So then the next step we wanted to do, we have this kind of a rabbit. We collaborate with Aaron Holden and Alan Benson in this to get this 3D DTMI scan, get this whole geometry, and also this fiber orientation. From here, we use this one slice of this whole heart. We have this two-dimensional whole heart model. So then we can simulate this kind of initiation and the conduction of these exciting waves. Then we calculate the ECG. So for here, the sinusoidal node in this region, these two are the atrium. So this point fiber running through the ventricle. Then here we have this sinusoidal node for this fast pathway and the slow pathway. So this is what we've done so far. So I hope I have convinced you this heart is complicated, but it can be reduced into a one-strand model, which incorporates a kind of heterogeneity in the heart. And with the whole heart model we have constructed is well validated by the experimental data at multi-scale levels for this molecular level, ion channel level, cellular, and whole organ levels. Okay, so the model successfully predict the effect of acetylcholine and on ECG part, and also this show this correlation between the two. The next step we wanted to do is to get this 3D whole heart works with consideration of muscle contraction and fluid dynamics. In parallel in the lab, we also construct a whole heart model for human, canine, and mouse. Okay, I'll stop here. Thank you very much for your attention.
Time for a quick question before we have tea.
Quick question. It looked a little on your EKG.
Yeah.
It looked a little like you had a left bundle branch block morphology. And I noticed that when you showed your simulation,
Yeah.
the LV was a little bit slow to activate, which was consistent with that. And that gets back to Natalia's question,
Yeah.
which is how variable is this in terms of variability in the actual details of the Purkinje structure?
Sure. What the point fiber we put here is just kind of cartoonish. We Mark in his lab just got this structure of this point fiber. We haven't got time to incorporate this point system in the model yet. So the point fiber we did there is kind of by arbitrary. I agree with what you said, but since this is two-dimensional whole heart model, it's just the preliminary data. So we can look at it into systematically how variation in the point fiber affect this ECG. So this is something we can do in the next step. Yes.
Okay, we should move on to tea. But before we do that, Nick has reminded me there are quite a few people who haven't put posters up yet. So if you've brought a poster, please could you put it up during the tea interval, especially if you're an early career researcher. And the second thing I'd like to do is to thank, just want to modify that,
In session 1 of the posters.
in session 1 of the posters.
Then please put your poster up.
Okay, the second thing I'd like to do is to thank all our speakers, especially for keeping to time, and we'll be coming back here at